Okay. So last class we have done until Sn. Okay. So some properties of Sn, how to calculate the properties of Sn. That's all we have done till now. Now we will start alternating group. So this will be alternating group. Okay. And we denote it like this An. Okay. So first let me define the alternating group. An is nothing but all such sigma belongs to An such Sn such that sigma is even. We have already defined what is even permutation and what is odd permutation. If you remember that if a permutation can be written as product of even number of even number of transposition, then it is called even permutation. And if it can be written as the product of odd number of transposition, then it is odd permutation. What is the order of An? This is nothing but n factorial by 2. Okay. Now the interesting fact is this forms a group. This forms a group under composition. As you can readily see that sigma even, if and only if sigma inverse also even. And identity equal to sigma compose sigma inverse. Okay. And you can check. This is easy. That it forms a group. Okay. Okay. And the cardinality of n is n factorial by 2. I am not going to prove this. This is a standard result. And it is, you can find the proof of this in any standard book. Okay. Now, from the previous knowledge, tell me this question. Which is the least possible order in A10?
One.
What, please?
One. I mean the order of identity, since identity belongs to it.
So 1 as order of identity equals to 1. And what is the greatest? What is the at most possible order? What is the highest possible order? Anyone? Please tell me. What is the highest possible order? We have done, right? What is the order of SN, element of SN? What is the order of element of AN? Not AN, but it is an element of SN, right? So the order property will follow from that. So what is the highest possible order? So this is question mark. Okay.
21.
21. So how?
I mean partition 7 3. So
7,3. So 7 is odd cycle, so it is even permutation. 3 is odd cycle, so it is even permutation. So that their total even times even is even permutation. Okay, it belongs to A. Yeah, it will be the case. Good, because 8 2 will be not possible, and the 9 it is also not possible. So yes, very good. So 7 3 is the partition, is the most possible order of the element. Okay. So partition 7 plus 3 and LCM of 3 comma 7 equals to 21. So 21 is the highest order possible. Again, one more thing, SN can be generated by 1 comma 2, 1 comma 3. Sorry, this will there will not be any comma inside. 1 2 comma 1 3 up to 1n. And you all know the meaning of this, right? We have already stated in our first class that what did we mean by this first or second class generated by S. So this is Sn is generated by this. Anyone can give me any proof? Hence is used that every element of Sn can be written as product of transposition. We have also shown this. Just use that fact. So everyone, please try to participate in the problem solving. Pias is telling everything. Others also please try, because otherwise, if I solve everything, it will not be any profit for you all. Okay. And if you all participate, then I can also fast. I can also go fast, and then you will learn many things.
Sir, I think if I try to write any transposition ij for I less than j, then it can be written product of 1i, 1j, and 1i.
Very good.
If ij is not equal to 1, otherwise if 1 of I and j equal to 1, then it is in that set already.
And ij not equal to 1, of course. If I and j, one of them is 1, then it is itself are transposition. So there is no problem in that. Okay. And this is of the form this also. And if ij other elements other than this, any other transposition of the form ij, then you just write it like this. And there will be no problem in ij not equal to 1. It is enough. I not equal to j, I less than j. Because if one of them is 1, nothing harm in that, right?
I think if one of them is 1, then the transposition 1 I, does not mean anything. So I mean,
Then
then it
is
would not be a 2 cycle, I think.
it itself belongs to this. It itself belongs to the generating set. So there will be no need of writing in this form. It's okay. But if I equals to 1, you are writing 1j, right? Then this is like 1 and 1i. So this is nothing but the single 1. And this is 1j. And this is 1i, just single 1. So ij equals to ij. It's trivially satisfied. And same case for j. And if j equals to 1, what will be that case? 1i and 1i. Yeah, yes. Okay. If j equals to 1, there may be some problem. Okay, so better to just take I comma j not equals to 1. I comma j not equals to 1. If I comma j, one of them is 1, then it is done itself. Itself is belongs to this set. So it itself in that set. So nothing we want to show. If there are other types of element, other types of transposition ij, there are different types of transposition, then we can write it in this form, this type of transposition. Okay, so this type of transposition generates the whole SN, because this types of transposition generates any type of transposition. This was our motto, that these types of transposition generates any types of transposition. And we know that every elements of SN can be written as product of transpositions. So if we can generate any types of transposition, then it is enough to generate any element of SN. So that was our target. And we have already shown that we can generate any types of transposition by these n elements only. Okay, so SN is generated by this set. Now, a very important thing to observe, that AN is generated by all 3 cycles. For n greater than equals to 3. Okay, proof, do yourself. Same technique. Just you have to write 3 cycles and 2 cycles and 2 cycles and 3 cycles just repeatedly. So AN is generated by all 3 cycles. So it is important thing to observe that if a subgroup of SN contains all 3 cycles, then it is either AN or SN. Can there be any subgroup question? Can there be any subgroup between AN and SN? Proper subgroup. That means just write like this: AN properly contained in H, properly contained in SN. Can there exist?
No.
No. Why?
If each contains n properly, then H has at least one odd permutation content in it.
Hmm.
There is a result that every subgroup of SN either all of its elements are even permutation or equal number of odd permutation and even permutation are there
Hmm.
in that subgroup. So
Okay.
since
Yes, you can also tell from that that if there exists a tau, let's say, and tau belongs to H, but tau does not belongs to an, then let an equals to sigma 1 up to sigma, let's say k, then just multiply it with tau. Just find tau times an, just like this. Sigma 1 tau, comma up to sigma k tau. And this will be distinct and this will be odd permutation. So
so
there will be.
tau in I think tau sigma 1 tau dot tau sigma 2.
Okay, just I just
Also
did it like
right.
this. Anything you can do, multiply, post multiply, or pre multiply, they will be odd permutation. Okay. So what you are telling, this is just two line proofs. Okay. But can you tell me, can anyone tell me with order property? I have already stated what is the order of AN, and you know that what is the order of SN. We don't need that proof. This is just like for one second proof that there can't exist any subgroup like this.
So since H is a subgroup of SN,
Hmm.
by Lagrange theorem, order of H divides factorial n.
Hmm.
And since n is a subgroup of H, so factorial n by 2 divides order of H.
Hmm.
So
Exactly.
now, if H is a proper subgroup of SN
Hmm.
uh,
Hmm.
properly contains n,
Hmm.
then cardinality of H is less than factorial n and would be greater than factorial n by 2.
Hmm. This will follow, but this is not
So
possible with these two conditions simultaneously satisfied. So either it has to be n factorial itself, or it has to be n factorial by 2. That means either H has to have to be an itself or Sn. Nothing else can be possible. Okay. Everyone is okay with this proof, or there is some problem? If there is some problem, you can tell me. Don't hesitate. Okay. Another question. This important question many times asked many competitive exam, that A squared A belongs to G. G is the group HB this set. Then H, this means normal subgroup. Okay. Normal subgroup of G. True or false? Try this. Try this. I'm giving you 2 minutes, 3 minutes. Try this and tell me. If you have done already, you can tell me. Okay. So no answer. If G is abelian,
Then it is normal subgroup.
So if G is abelian, then done. If not, then try with. So the problem is here that if you try the first non-abelian group in our mind is S3. So everyone, when they try to find some counter example for non-abelian group, they try with either S3 and if infinite group, they try with matrix group like this. But here the problem is if you try for S3, even S4, even S5, then the statements will be true. In all of the cases, it will be a subgroup, normal subgroup. So this is an interesting observation. Try this, please try at your home, okay? You have to just do calculations. Try with S3.
Sir, in dihedral group or quaternion?
Yes, it can be. You have to find the age. I am just telling for S symmetric group case. Okay. So for S3, try with S3, S4, and S5 in place of G, of course. Okay. Then age will be equals to A3, A4, A5, interestingly. And they all are normal. And now I come into your point. And what will be what will you find for dihedral group? D8. There are total 5 elements of order 2 in D8. 5, no. There are total 6 elements. 6, not 5. There are 5 elements. A square, B, AB, A square B, A cube B. That's all. 1, 2, 3, 4, 5. There are 5 elements. And A and A cube are of order 4 and identity of order 1. So if you square, what will you take H? if you consider H, then this all things becomes identity after 2 times operation, and these things, this will become a square, comma, and this will be also a square, and this will be identity. So identity comma a square, this will be 2 order, and again this will be normal subgroup. Is it normal identity comma a square? Anyone? Identity comma a square? Okay, I will come into this. I think I have not give you details about dn, okay, or d2n, so I will not ask any question. It may be you have not very good grip in this part, but I will come in it. It will be normal, okay, because if anybody know that b inverse, this will be equals to a inverse in d8, in d2n, you can say, or b to the power n, you can a to the power minus n, you can. So if you write like this, b square b inverse, it will be a to the power minus 2. So if you say g square g inverse, that's all. And you all know that if H is a normal sub, H is a subgroup of unique order. Let's say like this, K be a subgroup. We will come into this part, but we will come into this part after automorphism. All this is many fast. This will break my rhythm, but okay, I just, somebody has asked this question, so I am just writing. K is a subgroup of H of unique order, and H is normal in G. Then K is normal in G. Is it true? Or the other way? I am asking both questions. K is normal subgroup in H, and H is unique in G. Unique in G means unique order subgroup. There is no other subgroup of G of which is equals to order of H. Okay. Unique in G, then is K normal subgroup of G. Both of this is question for you. Tell me. K is a subgroup of H. Huh? Yes. Yes, anyone was saying something?
Sir, are those orders considered here? I mean, the order of each considered here is finite or infinite?
What will be the case for infinite? There is no meaning for this question, right? In infinite case.
But in infinite case, we can
All finite, all finite,
consider.
all finite, all finite. When we are talking about some order in some question, then it's mean we are talking about infinite case, finite case. Otherwise, when there is no mention of order, you have to take the infinite case, because that is the general case. But when it is mentioned about order, the 99.99% case will be they are considering finite case. Or they will not write order, they will write infinite order, they will mention. Which one of this true? Or there is no one true, or the both true? Anybody try? And you can prove it. There is no need of anything what we have not studied. There is nothing, no such concept needed for this proof. K contained in H, K is unique order subgroup, and H is normal in G. Okay, so for your all to simplify, I am removing this. Just prove this one. Prove this. Prove this thing only. There is a subgroup of H of unique order. We are talking all about finite thing, and H is normal in G, then K is normal in G. I'm telling you this is true statement. Okay, now prove this.
Because GK G inverse is equal to K.
GK G inverse equals to K. We have to show this.
হ্যাঁ মানে ultimate ওটাই হবে, মানে যেহেতু K টা H এর সাবগ্রুপ,
আচ্ছা,
তো GK G ইনভার্সটাও H এর সাবগ্রুপ হবে কারণ H নরমাল।
GK G inverse containing GH G inverse, which
হ্যাঁ
is
তো আর
equals to
এই হ্যাঁ আর GK G ইনভার্সের অর্ডারটা হচ্ছে K এর অর্ডারের সেম হচ্ছে। তো অতএব যেহেতু K টা ইউনিক, তো GK G ইনভার্স ইজ ইকুয়াল টু K, হেন্স ইট ইজ
Yes.
নরমাল।
Yes, as K is unique order subgroup. Right, so this is normal. So this is a very important statement. Okay, K is subgroup of H of unique order, and H is normal in G, then K is normal in G. Now can you tell me that identity comma square is D8? Question. Now tell me identity comma square is normal in D8.
Identity comma square is subgroup of the group generated by A of
Yes.
unique order of 4, and that group is normal in DD4,
Yes.
I mean D8.
Exactly. Exactly. So now apply this. And why this is unique? You don't need to know. This is cyclic group, and this is group of a subgroup of a cyclic group. And the fundamental theorem of cyclic subgroup, for any cyclic group, For D divides order of n, there exists an unique subgroup of order n, order D. Now to order there will be a unique subgroup, and that unique subgroup is this of order 2, as this is cyclic group. So this is a unique subgroup of this subgroup of D8, and this is normal. This is normal because index 2 subgroup is also normal. Always normal index 2 subgroup. So now apply the previous theorem. So you can see that in competitive exam we used to apply tricks and techniques all times. These are concept, but you have to bypass the calculation, right? If you want, this is easy, this is nothing, but you have to show that G square G inverse belongs to identity comma S square. Yeah, for all G belongs to this and that. Okay, just you have to prove this. But for all G, this is checking. But there is shortcut for that also. There is shortcut technique. But I am just saying that you don't need to do this. You can bypass all those calculations. So there is many things you can bypass. Okay, so these small techniques are very important in competitive exam. Okay, now come to our main question. H equal to A square, A belongs to G. So H equal to A square, A belongs to G. When G is non-abelian, what will be that case? Non-abelian. Okay. So now we have already told you that we have already observed, or I have already said to verify that for S3, for G equals to S3, S4, S5, H will be equals to A3, A4, A5. Just check. This is HW, okay? And now for take G equals to H6. Now G equal to H6, then H equals to sigma square such that sigma belongs to H6. Now I am claiming that this is not a subgroup of H6. Claim H is not a subgroup of S6. Can anybody give me two elements such that they belongs to H, but their composition doesn't belong to H? Try. I am giving you 2 minutes, 3 minutes to think about it. So no progress. Okay, let us try to see that are we able to do it or not. So try like this. Take sigma 1 as 1, 2, 3. This is equal to tau 1 square belongs to H. What is tau 1? I will not tell you. You have to find. Because you need to find this. Otherwise, you will not be able to solve in exam. You have to have strong grip in this type of computation and intuition. 2, 3, 4 and 4, 5, 6. Again, this is equal to tau 2 square belongs to H. What is tau 2? That's why previous day I gave you the homework like that type of things. But find sigma square equal to these. Find sigma such that sigma square equal to these. These type of things. Now find sigma 1, sigma 2. This will be 1, 2, 3, 2, 3, 4 and 4, 5, 6. And this will be equals to, you can see that this will be equals to like this. And this is not equals to tau square. For all tau belongs to S6. Why? Again. So sigma 1, sigma 2 does not belongs to H. So H is not a subgroup. So there are 3 questions. This. It is tough to find counter example, but I can solve these 3 questions now, and that will not take as much time. That will take 5 or 6 minutes maximum if we solve elaborately. If I solve elaborately now, but that will be not for any help for you all. You must try in your own that how I am claiming that this will not be the case. I have given you the example, I have given you the setup, all things. Now you just have to verify that this is true. And to verify this is true, you just need some concept of S6, some theorems of SN, some theorems of SN, some calculation, some manipulation, some products rule of SN, nothing else. And if you do in your own these things, then it will be good for you. Because we will solve many more tough problems. And if you can't solve, I am here always. Okay, you can tell any time. Even in next class, I can show you. But I just want you to try this. Okay, so Sn is non-abelian for n greater than equals to 3. So of course, n is non-abelian for n greater than equals to 3. Sorry, n greater equals to 4. Because we know Sn is non-abelian. Yes, A3 is cyclic for n greater than equals to 3. But An is non-abelian for n greater than equals to 4 as A3 equals to identity 1, 2, 3, 1, 3, 2, which is cyclic. Now, some important thing.
Sir, how does the second proof come? I mean, the non-abelianness of n, how does?
What? Please? Sorry, please repeat.
How is n non-abelian for n for 4 onwards?
Sn is non-abelian for n greater than equals to 3, right? We have already shown. In previous class, we have already proved Sn is non-abelian.
Yes.
And An is subgroup of Sn, right?
Okay, but a subgroup of a non-abelian group
The group
can
may
be
not be
abelian.
non-abelian, right? If you see the proof of Sn is non-abelian, and there if you see the construction of our case, what we have constructed. I don't have the previous thing.
Actually, those were the single transposition, so those does not belong to AN. So I think those proof won't work for AN case.
Yes, but they are just transposition, and they don't just commute, right? We have check, right? Like this type of things, just IJ and where IK, this type of things we have just constructed. And if you just add two more things, and this will be enough. Okay. I will construct now. Okay. Just I have to see how I constructed for Sn case. Okay. I will prove this. Don't worry. Just I am trying to say that the same conditions will be followed. Sn is non-abelian. We have shown just like that way. We can show that An is non-abelian. The construction will be more or less just we have to apply some trick to make it an element of An. But the construction will be the same. But okay, I am showing you. Don't worry. So center of Sn is only identity for all
For
n.
AN, it equal to
Huh? Yes.
yes, sir, that
Mhm.
is the that's what
And center of An is also identity. N greater than equals to 4. Okay. And there is one more important group which is K4. Anyone know this group? This will be identity 1, 2, 3, 4, 1, 3, 2, 4, and 1, 4, 2, 3. This is similar to some kind of group you all know. Can anyone tell me what this group is? This is normal subgroup of A4.
Z2 cross Z2
Yes, this is same as Z2 cross Z2. Okay.
planes 4.
Planes 4 group. We call it planes 4 group. Okay. And this is normal subgroup of A4. This is some interesting fact. Some of those. Center of Sn is identity. Center of An is also identity. And K4 is the subgroup given here. And this is normal in A4. Okay. Okay. So now the most important part of competitive exam. Okay, I will prove this. Okay. I will prove at the end. Okay.
So I think the proving the last statement would ensure that N is non-abelian since the identity is trivial, so it can be abelian.
Please again. What are you saying?
I think if we can prove that the center of N is just identity for N greater equal to 4, then N wouldn't be abelian for N greater equal to 4.
Yes,
I
of
think
course,
proving this is enough.
but you can I think you can intuitively think that this will be more difficult than this. The first statements will be more easier because if you know that you all know that if we take like this 1 3 1 2, what will be this? Can anyone tell me? What will be this? 1 3 times 1 2. Make the product and tell me. Yes.
2 3 1 2
1 2 3. And what will be this?
One, 3 2.
1 3 2. Okay. Now the thing is, they both will give you multiplication up to identity, right? If we producted 1 3, yes. So we have to we can't think it like in S3 we have to take at least S4 because if
A3 is abelian.
A3 is abelian, so there will be no example for that. We have to think for at least S4. So that's why I am telling that you have to construct it. So, but the construction for this will be easy, but this is more. We need more thing. Even for this we will need some more thing. We can't prove it so much easily. Maybe we need some automorphism and some isomorphism. Okay, so that's why I'm just coming into this part, that so we have to first go into homomorphism. Otherwise I can't do much thing to prove, because I have no tools until I do homomorphism. Okay, so what is homomorphism? You all know that for G1 G2 belongs to G, for all G1 G2 belongs to G, f of G1 G2 will be equals to f of G1 dot f of G2. Okay, then f G1 to G2 is a homomorphism. So just ignore my definition. Okay, this is not, you all know that this is crash course, so I am not defining it like the bookish way. Okay, I just want to remind you that what is the definition. So if G1 to G2 is a homomorphism if for all G1 G2 belongs to G1, f of G1 star G2 equals to f of G1 star f of G2. Okay, and some consequences of homomorphism I will give you at isomorphism. So this is homomorphism, so isomorphism. So what will be the isomorphism case? Isomorphism is nothing but homomorphism plus bijection. If G1 to G2 is called an isomorphism if it is homomorphism and it is bijection. Okay. So these two things are there. Okay. Okay. So now the important thing, which is properties. This is very important. Very, very, very important. Okay. You will need many this type of things. Okay. T G1 to G2 is an isomorphism. Isomorphism, then isomorphism, then the first one is identity goes to identity. The second one is T of A inverse equals to T of A whole inverse. The third one is T of A to the power n equals to T of A whole to the power n. And this is true for all A belongs to G, N belongs to Z. I am not writing that. Okay. AB equals to BA if and only if TA TB equals to TB TA. So I'm not writing for all B something or for all A satisfying this. Okay, T of ZG, center of G1, okay, equals to center of G2. So there are many consequences. Okay, so G1 is abelian if and only if G2 is abelian. Seven, order of T of A equals to order of A for all A belongs to G1. Okay. Eighth one is G1 equals to generated by A if and only if G2 equals to generated by T of A. Okay. Now this is the most important, or I would say many times we need this in exam, that if B belongs to G1 and M belongs to natural number, then the number of solution of the equation
X to the power m equal to
x to the power m equals to b in G1 is same as number of solution of the equation x to the power m equals to tb
in
G2. Okay, so this is many important, very important. And once we start solving problems, you can see that we will use many times this thing. So just quickly recap or write down. I will go into next page.
Sir, I think first three properties
Also holds for homomorphism.
Huh.
Okay, so please just note down or take screenshot. I'm going into next page. Okay. So the 10 is H subgroup of G1, then this subgroup. I am writing this. Okay, this means subgroup. I'm not. Then TH equals to this. H belongs to H is a subgroup of G2. This is also true for homomorphism. I'm not writing for homomorphism all these things. You all know you can find homomorphism things anywhere. If K contained in G2, then a subgroup, okay, not content. T inverse K, this is also true for homomorphism. A belongs to G such that TA belongs to K is subgroup of G1. If G1 is finite, then G2 is also finite, and number of elements of order K in G1 equals to number of elements of order K in G2 for all K. So this is again very important. Okay, so now I will give you question. You have to solve. C star isomorphic to R star. Second, A4 isomorphic to D6. Third one, D4 isomorphic to Q8. I guess you all know Q8. Okay, so I will ask you after 2-3 minutes all the proof. Okay, so try to solve. If anyone have already done, you can tell me, okay? So we have written all those properties, just try to apply those properties.
Sir, D4 means is diagonal group of order 8 or 4? I mean,
Order 8, order 8. DN means to order 2n.
some books like the David Foote uses the notation D
Yeah,
suffix.
many books use many notation, so there is no problem in notation. Okay. In question paper, there will be given that D2n means the ideal group of order 2n or DN means the ideal group of order 2.
এটা তো মানে ট্রু ফলস কিনা বলতে হবে, তাই তো? এটা তো
Yes, yes, of course.
আচ্ছা,
True,
তো
false.
ফার্স্ট আর সেকেন্ডটা ফলস হবে।
Now,
কারণ সি স্টারটা মানে সি স্টার থেকে আর স্টার যদি আইসোমরফিজম থাকে ধরে নিচ্ছি, তাহলে T1 ইজ ইকুয়াল টু 1, তাহলে টি আই স্কোয়ার মানে টি আই এর হোল স্কোয়ার যেটা, সেটা টি আই স্কোয়ার, এটা হচ্ছে টি মাইনাস 1, যেটাকে
just 1 equals to 1
হুম
imply T.
নো, আমি লিখছি যে টি আই এর হোল স্কোয়ার
হ্যাঁ,
সমান হচ্ছে টি মাইনাস 1
T minus 1
সমান হচ্ছে মাইনাস 1।
minus 1.
হ্যাঁ, আর টি আই স্কোয়ার মানেটা কি? টি আই এর হোল স্কোয়ার,
এটা করতে গেল।
কারণ আইসোমরফিজম তো তো
তার
টি
কারণ হ্যাঁ আইসোমরফিজম, বাট এটার চেক চাই। T of -1 equals to -1 হয়, হলেও তার কারণ বলতে হবে।
অপারেশনটা তো এখানে মাল্টিপ্লিকেশন,
মাল্টিপ্লিকেশন,
ও
নট
আচ্ছা
অ্যাডিশন। 1 এর
আচ্ছা,
-1.
সরি মাল্টিপ্লিকেশন।
Try to use
in
property
C star there are at least 4 solution of the equation x to the power 4 equal to 1, namely plus minus 1 and plus minus I, but in R star this is not exactly 2.
x to the
So
power
those
4
are
equal
not
to 1 has 4 solution. So I minus I 1 minus 1. That's why I am giving star in 12 and 9. If you see, we will use many times these two property in C star. But x to the power 4 equals to T of 1. Here we are using T of 1 equals to 1. Identity goes to identity. What you have told in first line. Okay. So T of x to the power 4 equals to 1 has only 2 solution. That is 1 comma minus 1 in R star. So implies C star not isomorphic to R star. We are using property 9. Okay. So now yes, try the second one.
সেকেন্ড ওয়ানটা মানে A4 এ অর্ডার 6 এর কোনো এলিমেন্ট নেই, বা D6 এ অর্ডার 6 এর এলিমেন্ট আছে।
D6 এ order 6 এর element আছে, because আমাদের D12 means D6 means cardinality of D6 equals to 12. Dn means 2n. This is our notation. And we all know that Dn either generated, the subgroup generated by A equals to order 6 order, and the B order of B equals to 2. Okay. So therefore, let me write this. D6 has an element of order 6. Somebody write it like R and somebody like write it as A, so that doesn't matter at all. But A4 has no element of order 6. Why? The maximum order element of A4 is the maximum order of element A4 can be, even for S4, the maximum order can be, why A4 doesn't have the element of order 6? Why? Why A4 doesn't have element of order 6? Please.
Maximum order element to A4 is 3, right?
Yes, S4 itself has maximum order element 4, right? Because S4 it can be 2 or a 4 cycle or a 3 cycle or a identity element or 2 cycle. Otherwise, there are no types of elements in S4, right? So S4 itself can have maximum order of an element is 4. Are there any other higher order possible for any subgroup of that group? S4 itself has maximum order element is of order 4. So S4 itself has a maximum order element order 4. So A4 is subgroup of S4. So how can it be possible order 6 elements is there? And again, so this is a thing, okay. And you can also check the number of elements of order 2 are not same for both the cases. I am just writing it here. You can check in your home, at your home. Check number of elements of order 2 for both the group. And the third one?
In Q8, there exist at least 3 elements of order 4, IJK. But in D,
6 elements.
in D6, this is exactly 2.
So number of elements, number of elements of order 4 in Q8 is 6. There I minus I, J minus J, K minus K. These are all elements. Okay. And number of elements of order 4 in D8 is 2.
D6,
D6 or D4, okay.
D.
D4 is 2.
5, 4.
5 or 4. Because there I will just tell the structure of D2N because there are lots of things to say about it. So okay, you all know that these things, okay, so they are not isomorphic. Again, which property? Property 12. Okay, so D4 is not isomorphic to Q8. Okay, so let me discuss the structure of D2N. Okay, DN or D2N. So we write it like this: DN or D2N. Most of the exams clarify this notation. Okay, and otherwise from question it can be readily understandable. Okay, what does it mean? So DN is nothing but this is generated by A comma B such that order of A equals to n, order of B equals to 2, and
B inverse is A inverse.
B inverse is A inverse. So this is the statement. But this is the group DN, okay, generated by this thing. Now, if we look into the structure of DN, this will be like this. Order of A is n. That means identity A square, A cube up to A to the power n minus 1 is there. And then there will be elements of the form B. Just multiply this AB, A square B, A cube B, and up to A to the power n minus 1 B. So you can readily see that the cardinality of Dn is 2n. And you can check these are the all elements. Interesting fact. Order of A to the power IB equals to 2. Order of B is 2 given, and order of A is n given, but order of A to the power IB is also 2. Check.
What if I is a multiple of n?
I is
Okay. Is it geometrically is told as reflection or rotation, like things?
yes. D4 is nothing but D4 is quadrilateral. These things just 1, 2, 3, 4, just rotation of 90 degree. So A means rotation of 90 degree and B means reflection. So there are 3 types of reflection is there, right? There are 3 types of symmetry is there. These, and these 4 types of actually. These 4 types. And but we can see that for us, one reflection will be generate all of them. We need 4 rotations. 1 times rotation, that means single A. 2 times rotation of 90 degree, that means A square. 3 times rotation, that means A cube. And 4 times rotation, that means A to the power 4, or you can say identity, no rotation, same things. And we have 4 reflections, but we don't need 4 reflections. If we take 1 reflection and the 4 rotations, their composition will give you all the symmetries, all the rotations and reflections possible with these 4 rotations and 4 reflections. Okay, so 1 reflection is enough. That's why we take A square A to the power up to A to the power, and for B we are enough. Just identity and B is enough. No reflection and single reflection is enough. But okay, these are all part of conceptual things. This will not need for problem solving. Okay, so order of A to the power IB equals to 2. Use this, you can check. And and this is always a cyclic subgroup, as you can see. Cyclic subgroup of Dn always. And third one is This is always indexed to subgroup, so this is not normal. This is normal subgroup of DN. 4-1 is center of DA. What will be center of DN? Anybody know?
Identity if n is odd and identity comma a to the power n by 2 if n is even.
This center. Okay. So this is the structure of DN. Oh, I guess 12. It's near to 12. So I just want to end with the example Saurabh Sadhukan asked me for A4 is non-abelian. A4 is non-abelian. A4 na An is non-abelian for n greater than equals to 4. Okay. So what will be the example? We have to construct the example. Okay, just take this in A4. 1, 2, 3, 2, 3, 4. This will be equals to 1, 2, and 3, 4. And take this 2, 3, 4, 1, 2, 3. And this will be equals to 1, 3, 2, 4. Okay, so clearly 1, 2, 3, 4 not equals to 1, 3, 2, 4. As here 1 goes to 2, here 1 goes to 3. So it can't possible. The two map are same means every element goes to the same element, right? So they are identical for each point. Okay, but here 1 goes to 2 and here 1 goes to 3. So two maps are not equal. And you can see that these things are these things, so they are not computed. So A4 is non-abelian. So these elements are A4, right? A4 is non-abelian, but it is enough. So An is non-abelian. Can anybody tell me why this is enough?
N greater equal to 4, so these cycles are always in An for every n greater equal to.
Yes, of course. So n greater than equals to 4, we can always treat it as elements of n where n greater than equals to 4. So An is non-abelian for n greater than equals to 4. Okay, so we are done. So now we can jump into more rigorous thing. So just let me give one more exercise. It will be
হচ্ছে স্যার এটা কি ওই গ্রুপ অ্যাকশন থেকে কি আমাদের এটা মানে স্টার্ট হবে মানে কোর্সের যেটা মানে মানে যে এটা এগুলো তো অনেকেরই তো জানা মানে এগুলো তো আগে থেকে
ক্লাসিফিকেশন তো আমরা ততক্ষণ করতে পারবো না যতক্ষণ না আমরা সাইলো আর গ্রুপ অ্যাকশন খুব ভালোভাবে জানবো, রাইট? তো ওটা তো করতে হবেই, মানে আমাদের টার্গেট তো মেনলি ক্লাসিফিকেশন করা জিনিসপত্র।
হ্যাঁ মানে ওগুলো কি রিগোরাসলি হবে তো? তাই
rigorous means this is not a course for theorems and concepts. Okay, this is a course for problem solving. So problem solving, what I am just doing, just writing the theorems or writing the things to remember to solve the problem, then we are solving the problem, because it is not possible to take 1.5 hour class in a week and just for 5-6 months and to solve to teach you all the concepts of group action and silos and all the things with problem solving. So this is not possible. This is much short time. Okay, 1.5 and 2 hours. This is not possible. And this course is for problem solving. This name is for problem solving. So again, just let me stop the recording first, then I can tell you.